Hello class. Today we're going to be looking at section 12.2. It's our last lesson. And section 12.2 is about two-way categorical data. It's an ANOVA test. We're assigning 12.2 assigned today, Wednesday, April 29. It's due next Monday, May 4. That's pretty close to your final, so you may want to, even though it's not due till Monday, you might want to get it done here this week, all right? But two-way categorical data, that's different than 12.1, which was one-way. What I mean by two-way is you got some variable going on up here and some variable going on over here. And we have, obviously, multiple levels of each variable. That's what we mean by a two-way categorical data. It's going to be similar in some ways to 12.1, except that it measures something totally different. But in terms of carrying out the test, it's going to look real similar to 12.1. This slide is going to kind of give you a summary of the difference between 11.1, 11.2, 12.1, 12.2. Section 11.1 and 2, we looked at a one-way multiple mean, not proportions, not categorical data, but a mean. We tested to see if there was any difference between means of 3 or more populations. That was back in chapter 11. We tested to determine if there was any difference between proportions of 3 or more. So we weren't looking at means, we were looking at proportions, 3 or more. We wanted to see if they differed or if they were different from some other city, like we looked at Cleveland or something like that. Today, we're looking at two-way categorical. That's just like 12.1. Categorical means proportions. Again, an ANOVA test. We're testing, but now notice this. We're not testing if the proportions differ. We're testing, are they two variables? That would be like these variables A and B. Are they dependent with each other or are they independent? Big change here. A lot of people want to put these two in the same category, but these two are totally different. Okay, recognize that difference. We're looking to see if the variables are dependent or independent. Also, keep in mind, dependent means there's a correlation. Dependence means there's a correlation, not necessarily that one causes the other, not causality, but only is there a correlation. To help you understand what we mean by that, I would like you to guess on these following sets to see if you think they would be dependent or independent. We're just guessing here now. Just test your instincts. Do you think high school class rank and college GPA are related? Do you think that they are dependent or independent? I think a lot of different answers, but I'm here to tell you those two are related. If you get a better class rank, your college GPA usually is higher. They both go up together, they both go down together. They are dependent, they're related. Colors of eyes versus college GPA. Do brown-eyed people naturally get a higher GPA than blue-eyed people? And as you would have probably guessed, there's no correlation there. There's no dependence. They're independent of each other. They go up and down at random. ACT score versus college GPA. That's similar to the first one, high school class rank versus college GPA. If you get a better ACT score, are you likely more likely to have a better college GPA? Do those go up and down together? And the answer is yes. Not necessarily that one causes the other to go up or down. Usually there's an extraneous variable at work. In this case, it would be intelligence. Intelligence tends to get you a higher ACT score. Intelligence tends to get you a higher GPA. Not that that's the only case, because also exposure to the different things that ACT tests is also an extraneous variable. But here's dependence. They do both go up and down together. As one goes up, the other goes up. One goes down, the other goes down. In fact, these two have a higher correlation than these two. When we look at college GPAs, we're trying to see which ones we predict are higher. ACT score is a better indicator than high school rank, partly because high school rank has great inflation in it, and that can disguise how well they're going to do at college. ACT scores describes better how they will do at college. Level of weight versus college GPA. Do thin people naturally get a better GPA or lower GPA? As you may guess, no dependence. They are independent of each other. Ice cream sales versus level of petty crime. I may have talked about this before, so if I do, I apologize. But these, believe it or not, are dependent. When ice cream sales are up, so is the level of petty crime. When ice cream sales are down, so is the level of petty crime. They go up together, they go down together. They don't cause each other to go up and down, but they both are caused by something else going up and down. And that, of course, would be the temperature. When it's really hot out in July and August, ice cream sales are up, but also a lot of the juveniles are not in school. They don't have homework. It's warm enough for them to be outside, more petty crime occurs. So temperature causes both of them to increase. When it's January and it's 0 degrees, ice cream sales aren't as good, and the level of petty crime, most high school kids are not out on the streets as much. There's some, but not as much. So when it's January, both of them go down. When it's August, both of them go up. They're dependent. 40-meter dash time versus starting wide receiver in the NFL. They are very much dependent. Their inverse correlation, when your dash time goes down, your starting receiver likelihood or probability goes up. If you're like me, when you have a very slow 40-yard dash time, your chances of starting at wide receiver in the NFL is slim to none. It's not even that good. They go opposite, but they are dependent. Both of them move accordingly. This one goes down, this one goes up. They both either go opposite all the time, very much dependent. Quality level of singing voice versus color of hair. Do blonde people naturally sing better? Well, again, you might guess there's no dependence there. They are independent. Weekly workout time versus level of weight. Well, you might guess they are dependent. The more you work out, the lower your level of weight. They are opposite, but they are definitely dependent. They move in correlation with each other. Daily wake-up times versus desire of eating beef. Do people that early risers naturally eat beef more? The answer is they are independent. They don't affect each other. IQ score versus college GPA, very much dependent. In fact, this one is likely to be causal. The higher your IQ, the higher your GPA. One causes the other. IQ causes higher GPA. They are dependent, and that one happens to be causal. As I mentioned, this is how two variables compare to each other. Here's an example of a general chart. We have one variable up on top. It might be A. We have another variable going down the side, B. Could be color of hair and IQ. These are different cells. These would be observed cells. Notice that we have to have two subscripts. Notice this one, for example, gives you the row subscript, row 2, column 1, 2, 1. Over here, we have, for example, row 1, column 2. That would be the observed count in 1, 2. Row 1, column 2. This would be the entire total of the column 1. This would be the entire total of row 1. This is the total number of people that we asked or checked in our experiment. Okay? Here's the one thing you will like about a two-way categorical testing procedure. The null and alternatives are always the same. We say the two classifications are independent for the null. That's what we start off assuming, that there's no correlation. And our alternative, what we're hoping to show is that they are dependent, or they do have a correlation. If I have variable B and variable A, I might say variable A and variable B are independent. Variable A and variable B are dependent. That would be listing my two classes, and I'll model that later on. Here's the part you will like. Chi-squared is the same statistic. We're comparing categorical data, two-way. This is the observed count. These are the expected counts. It's the exact same formula that we had in section 12.1. It's just that we have a subscript that refers to two different columns and rows because I have a two-way table. My expected count, copy that down, my expected count is the row total. I'll put that over here, row total times the column total over total count. Row total times column total over the total count. You'll have to find those expected values in these different cells. Very similar to what you did in the last time. The last time it wasn't two variables. Our rejection region, our degrees of freedom, is slightly different. Last time it was k minus 1. This time it's got two factors, the number in the rows and the number in the columns. This is how many different levels of variable A, how many different levels of variable B. Subtract 1 from each, take their product, is your degree of freedom. Same chi-squared chart. Same chart that we used in section 12.1, but this is how you calculate your degrees of freedom. The expected value for each count, you'll be calculating that. Remember, we said it was this right here. Okay, row total times column total divided by total count. Well, where does that come from? I'm hoping that this slide helps you at least understand where we got that expected number of n. And I'm going to go I. Okay. Well, we take the total number of people that we're polling. This represents the probability that it's in that corresponding row. This is the probability that it's in that corresponding column. So I want the probability that it's in that correct column times the probability that it's in the correct row times how many I have total that I'm polling. The n's cancel here, and that's why you get RC over N. That's where the formula comes from. But what does it mean again? This is the probability that it's in that corresponding row times the probability that it's also in that corresponding column times the number of people that we're looking at. Some conditions. This is, again, if you're looking to run this kind of test for a thesis or dissertation or something like that. This is for two-way categorical data. N is the observed counts, which we've talked about. The expectation is at least 5. Once in a while, you're still able to run this. Still robust means still pretty strong a test if the average is 5. But we're going to look at today only that the expected count has to be at least 5. We're going to practice once right now with an example where you have just the numbers so we don't get tripped up in the actual details. Here, imagine we're testing to see if there's a relationship between 3 levels of variable A. That would be like A1, A2, A3, and 2 levels of variable B, B1, B2. I have a table made out in the next slide. Here's my 3 levels of variable A, 3 levels of variable B. I'm testing to see, are they independent or are they dependent? Total 50, total 100, total 33, total 37, and here is 150, right? So one of the first things we would need to do is to find the expected count of these 6 cells. Okay, not the totals, just the 6 cells. Remember that expected count for each of those. Recall that expected count was the row total times the column total divided by n. So what would I expect here for 13? I would have expected 50, that's the column total, times 33 divided by 150. This would have been 33, that's the row total, times the column total, 50, divided by 150. And I would calculate that out, and here, carefully, I'm going to round it off to the nearest number. Rounding it off to the nearest number. What would the 27 have been? Well, it would have been 80 multiplied times 50 divided by 150. What would this 27 have been? It would have been 37 times 100 divided by 150. I hope you see where we got all of those numbers. So we would have to calculate those 6 numbers, again, round it off to the nearest integer. For example, here's those 6 cells again. My expected count here was 22. It was 33 times 100 divided by 150. Gave me 22. I would have to do that for all 6 of those. It would look something like this. I put it in parentheses. You can check each of those out, and we rounded them off. I put all of those in a little smaller form on this slide. It's the same numbers that we had in the previous slide. Now comes the question we're going to determine. We're going to run the hypothesis test to see if there's any dependence between variable A and variable B, or are they totally independent? Here I got 13, I expected 11. It's pretty close. Got 20, expected 22. Pretty close, right on, right on. I'm going to guess here, I haven't even looked at this yet, but I'm going to guess that there is insufficient evidence to determine that there is dependence, that we're going to have to continue to assume they're independent. But let's run the test. Remember the null and the alternative. Variable A and variable B are independent, or I could say variable A is independent with variable B. My alternative is that they are dependent. Running an alpha test at 0.05, I didn't list anything else. Comparing multi-categorical data, same thing we had in 12.1, chi-squared statistic, not an F, not a Z, not a T. My rejection region, notice my degrees of freedom here. 1, 2, 3 levels, 1, 2 levels up here. 3 minus 1 and 2 minus 1, I take their product, that's 2 times 1, I got 2. I would have had 2 degrees of freedom on my chi-squared chart. Look at 0.05 column, that would have been the number. Okay, step number 3, you got to calculate. Take 13 minus 11, square it to make sure it's positive, divided by what I expected. 20 minus 22, square it, divided by what I expected. 10 minus 12, squared, divided by 12. Would have had 27 minus 25 over 25. And 27 minus 27 squared over 27. 53, the last one, minus 53 squared over 53. Notice I had a very small chi-squared. It's because what we expected, we were really close every time. Because it's a small chi-squared, it's not in the rejection region. I've got insufficient evidence to reject the null. I continue to assume variable A is independent with variable B. I just use variables A and B, so we would focus on the numbers here, all right? Again, if this isn't automatic to you yet, don't be afraid to pause, slide it back and run through it again. Maybe do it 2 or 3 times if it's challenging for you. Let's do one now that's maybe just a little more interesting, okay? The Journal of American Medical Association published results of a study of alcohol consumption relating to congestive heart failure for people above 50. This is 50-year-olds or more. And they have to have 2 or more risk factors. That would be the risk factors for congestive heart failure. Might be a genetic factor, it might be overweight, might be diabetes, might be smoking, a lot of possibilities, okay? But alcohol. Is there a relationship between alcohol consumption and congestive heart failure? Think about how you would answer that. Do you think there is a relationship, which means they're dependent, or is there no relationship, would mean that they were independent? We're checking at an alpha of 0.05. Here we go. Here's the data that Journal of American Medical Association published. They broke up the amount of drinking into just 3 categories. And of course, there's a lot of ways you can break up alcohol consumption. You could have this broke up into 10 categories. You could have it broke up into wine, have it broke up into beer, have it broke up into hard liquor, a lot of possibilities. They just went 0 drinks per week, 7 or less, greater than 7 drinks. Congestive heart failure, yes or no? Look at the size of the study. Pretty big numbers, 1,913 people. That's a lot. Okay, what do I got to do first? I'm hoping that you would say I got to get these expected counts for these 6 cells. This 146, it would have been 281 times 896 divided by 1913, rounded it off to the nearest number. This expected count would be 281 times 696 divided by 913, rounded off to the nearest number. This one would be 281 times 321 divided by that, rounded off to the nearest number. Here's what you end up getting for those expected counts. Okay? This one right here was total 696 times 1632 divided by 1913, rounded it off. Okay, put those same numbers on here now. Now we're going to run the test. Here are the numbers. Think about what your null and alternative should be. They're easy because they're always the same. I start off, my null is that they're independent. So I say the number of alcoholic drinks is independent with whether you develop congestive heart failure. I could have worded it, number of alcoholic drinks and congestive heart failure are independent. Number 2 is that they're dependent. These 2 are identical except one is independent. Don't get them switched up. The other one is dependent. I don't know how you want to keep those straight, but you put this one with the null and this one with the alternative, -3 out of 15. You messed it up. So they got to be in that correct category. Alpha level is 5%. We're comparing multi-categorical data, chi-squared. Rejection region, again, you wouldn't need this degree of freedom, but you would definitely need the rejection region. If you don't have the rejection region, -3 out of 15, okay? How do I get that? Well, 3 is 1, 2, 3 this way. The 2 came from 2 this way. Subtract 1 from both and multiply to get their product. 2 degrees of freedom, column 0.05 out of that chi-squared chart. Where do I get these numbers? I take 146 minus 132 and square it, divided by what I expected, 132. This one, 106 minus 102 squared, divided by what I expected, 102. 29, that's a big miss there. 29 minus 47 squared, especially when I had expected it to be 47, that's a major miss. That's a miss of 18 out of 47. Here, 750, 764, etc. Well, look, we get about 10. Our rejection region was anything over 6 here. We got into the rejection region. We got over our line in the sand. Again, the distribution of chi-squared is skewed. My rejection region is here. My line in the sand was 5.99. If I go over that line, I go past that, I'm in the rejection region. I got 10, that's way over here someplace. Definitely in the rejection region. Means I got sufficient evidence to reject the null that they're independent. I now conclude the number of alcoholic drinks in 1 week is dependent with whether you develop congestive heart failure. Most of you might have guessed that they are in fact dependent, but it will surprise you this. Watch carefully. It will surprise you this. It's not in the dependent direction that you think. Notice when I had more drinks, I expected 47 congestive heart failure. We only got 29. We had less congestive heart failure with more drinks. People that didn't drink at all, we expected 132. We got more than we expected. It's opposite of what most people think. Now, listen carefully. In no way am I trying to encourage you to drink 7 or more drinks per week. That is not the purpose of this. The purpose of this is sometimes it's a little bit more disguised than you think. There is correlation here. So we do say they are dependent with each other. As the drinks go up, the congestive heart failure goes down. They go opposite. They are correlating, but they're not what you think. They're not necessarily proven to be causal, all right? We're just saying that that's out there. Again, I'm not encouraging you to drink 7 or more. I'm just saying be aware of that. One of the problems that's also dependent with drinking 7 or more is it will trash your liver. It might be better for your heart, but it's going to do a lot of really bad things to your liver. Hence, maybe 7 or more is not appropriate for you to have. But bottom line, look at this once, the conclusion, sufficient evidence to say the number of alcoholic drinks is dependent with whether you develop heart disease. It just wasn't in the same direction dependent that we thought. Some words of caution about this two-way ANOVA test. On the average expected cell count, that would be if any of these red numbers were not 5 or more, we should probably not use this test. If the null is not rejected, we are not sure that they're independent. We just have not been able to detect it. Maybe it's because our alpha level was too low. We're not sure. It's basically if you're the type 2. We simply got to continue to assume that they're independent. We're not absolutely certain that they are. That's why we always use that phrase, continue to assume, when we have insufficient evidence. We're not concluding that they're independent. We're continuing to assume that they are independent. There's a different level of punch there with that overall statement. This is a biggie. Do not infer that one causes the other. Contingency tables analysis determines dependence only. It does not determine one causes the other. For example, higher ACT is dependent with college GPA. It does not mean one causes the other. It means that they both go up and down together. Intelligence causes them both to go up and down together, and also what level of subject matter they've been exposed to causes them to go up and down together. We cannot infer or believe one causes the other. To prove one causes the other is a much more challenging proof than a lot of people realize. It's not as easy as hypothesis testing. One last example. Consider the following accident report for 1,000, again, a pretty good number, young people during their first year. This would be just their first year of driving, age 16 to 17. This is from an insurance company in the state of Ohio. These are actual numbers. Test the alpha 0.01, that's a low level. It means we are really going to be certain if there is independence or dependence, or I should say if there's dependence. Alpha, that low means we're going to be really sure that we reject independence and assume and conclude dependence. If there's evidence that the variable of gender and likelihood of an accident in your first year, this would be at least one. It means one or more accidents or no accident during the first year. Male, female, okay? The age-old question, who's the better driver, right? Well, let's talk about that once as we go through this. What's the first thing you would do? I need to get the expected count in these four. There's only 2 divisions each way, so I have 4 expected counts that I would need to get. Each of those, this one, 154, the expected count would be 600 times the column total, 222, divided by 1,000, and I would round it off. This expected count would be 400 times 778 divided by 1,000. This one would be 400 times 222 divided by 1,000, etc. Well, I've done that. Here are those expected counts. Okay. Now we're going to test, is the likelihood of getting into an accident independent or dependent with gender? All right. So think about what you would do for your null alternative. They are the same. The null is always independent. Don't get them switched around. The probability of an accident is independent with one's gender. The alternative, what we're hoping to show, is the probability of an accident is dependent with one's gender. At a really low alpha level. So if we're going to conclude dependence, it's going to take a pretty good test to make that happen. We're comparing multi-categorical data, which tells the audience we got to go a chi-squared statistic. Get my degrees of freedom here from that value that I take 2 this way, minus 1 times 2 the other way, minus 1. That's going to give us 1. So I go to the very top row in the chi-squared chart, and I go to the column 0.01. That gives me that number. Where do I get all of these? I take 154 minus 133, square it, divided by what I expected. Take 446 minus 467, square it, divided by what I expected. Take 68 minus 89, square it, divided by 89. Make sure, again, you can come up with this number. You got to be able to do this on your calculator. Again, it's not designed to be busy work. It's to help you understand. We're looking at how far we're missing these. 10 is definitely in the rejection region, which means I've got sufficient evidence to reject the null. I now conclude the probability of getting into an accident from age 16 to 17 is dependent with one's gender. And what would we expect? Well, that's kind of what you'd expect. We expected 133, and we got 154 for the males. The males had more accidents than what we expected. The females, we expected 89, they only had 68. Does that mean causality? Well, again, be careful. It doesn't prove causality. It just proves they're related. Males and more accidents go up together. Females and fewer accidents go down together. May prove causality, may not. Some would argue it is causality. They would argue that male has greater amount of testosterone, which is more aggressive. They're going to be more aggressive at cutting people off, passing quicker, passing maybe when they shouldn't, changing lanes when they shouldn't. Females have less testosterone. They're going to be less aggressive. That would be an argument for causality. But here's one that would not argue causality. It would argue this. Males tend to drive more miles. And when you drive more miles, you have more exposure. And that's why you'd have more likelihood of an accident. It's why, for example, State Farm right now with this pandemic, State Farm is offering a credit back to their customers because there's fewer miles being driven by just about everybody, which means the likelihood of accidents goes way down. And that means State Farm, as would every other insurance company, make more money. So they're saying, we're going to give some of that back. That's one of the ads you see on TV frequently right now. Okay? So there's an argument for causality and one against it. But they can't argue this point. Males get more accidents than what you would expect. Females get fewer accidents. Again, I know all of you can come up with an exception, and you might know some male named Joe, and you say, Joe never gets into an accident. That's probably true for Joe. But these are averages. On the average, males will have more accidents than will females in that first year. I know some females that are not good drivers. You know some males that are good drivers, and vice versa. But we're talking averages. Insurance company base their premium partly on this average. They charge you more for car insurance if you're a male than you're a female. Is that gender bias? Yes, it is. And they're able to get away with it. We cannot always get away with that bias in some other areas of business. But in insurance right now, they are. Maybe in 10 years, there'll be enough males that are claiming that's discrimination and saying that all 16-year-olds should get the same premium. Females would probably argue that, or parents of females would probably argue that they want the cheaper rate. Parents of males would probably argue in favor of it because they want it to be a cheaper rate. They don't want it to be more expensive. All that is possible future things. But right now, you cannot argue males have more accidents than what is expected compared to females. They are dependent. That is all we have for today. We'll look at our review and talk about our final the next time we meet. But until then, have a good day.